So today we are going to cover blade pitch motion. In the last class we looked at blade lag motion, and this is lecture 19 of our helicopter dynamics course. I am Dr. Ranjan Ganguly. So here also we will assume that the blade is rigid and there is only one degree of freedom for this blade, and this is the blade pitch motion. So previously we presumed the motion to be flap motion and lag motion each separately, and now we look at the pitch motion separately. And as you know, the pitch motion is also known as feathering, and it takes place around an axis. There is also a torsional spring at the root, and this torsional spring basically provides you the stiffness for this problem. Now this is a top view of the rotor blade in pitch. So you can see here, this is the hub, there's the rotation happening here, this is the rotor blade, and here this is the feathering axis, and the blade essentially pitches around this feathering axis. Okay, and there is also a CG axis. It's shown here with the dotted line, and the distance between the feathering axis and the CG axis is given by x subscript I. Now this distance here is somewhat larger than usual, but I'm just showing it to point out that there is typically a distance between the feather axis and CG axis which may happen. So now if we look at it from the side view, we will see the airfoil section. And so when your airfoil section is like this, theta is 0, and then essentially the blade goes up like this. So this is the pitch motion or the pitching motion as we call it. And the blade pitch angle is known as theta, which is the notation we use for pitch, and this is also in the nose up direction, positive. Now let's define some notation. Theta is the pitch angle, theta subscript con is the control system command pitch, and this part of the pitch comes from the pilot. So theta minus theta control is the pitch change due to flexibility. Xi, as we discussed before, is the chordwise distance of the CG behind the feather axis. I0 is the mass moment round the CG per unit length. I subscript theta is the mass moment round the feathering axis per unit length. The relation is that I theta is I0 plus mxi square, where m is the mass per unit length, and k subscript theta is the control stiffness system. So with all these notations lined out, we are going to derive the equation of motion for pitch. And first, of course, we are going to look at the forces which act on a section. So this is a typical blade section in pitch. So now remember that there was a spring, a torsional spring, and this is the feathering axis here, this is the CG axis here. So essentially let us look at all the forces which act on this particular section, and we look at length dr, and that r is in the radial direction. So we start with one force is going to be there around the CG, that is I0 theta double dot dr, that is from your basic dynamics. Now because of this offset, there is also going to be a mxi theta double dot dr. There is going to be a moment term I theta rotation speed square theta into dr, and an force term here m theta dr. So this force term is due to the fluid mechanics forces, the m theta part. Okay, so these are some of the key forces which act, and of course there is the spring also, which also is a restraining spring, so that will have a k theta into theta component. And like I mentioned before, xi is the distance from the feathering axis to the CG axis. So let's write this all down once again so that we are able to derive the equation of motion. So we have the force mxi theta double dot dr, and the moment arm is xi because we are going to take the moments at the feathering axis. The inertia torque is I0 theta double dot dr. This is about the CG axis. The propeller moment is I theta, rotation speed square theta, and this is around the feathering axis. The aerodynamic moment is m theta dr about feathering axis, and the spring moment is k theta theta minus theta con. So we put minus theta con here because we are going to remove the control part and only consider the flexibility part. So all these forces outlined are pretty well known in dynamics except for the propeller moment, so we'll spend a little bit of time explaining the propeller moment. Now what you can think about is that there are two masses of size dm, so that's a very small mass, the d being the derivative nomenclature, and these masses are placed on both sides of the feathering location. So one is on top of the feather axis and one is below it. Now the chordwise component of the force which acts on each mass is going to be the mass into rotation speed square into the distance to the point. So distance to the point is going to be r square plus x square, square root of that, where x is the distance between the feather axis and this mass dm, and then this is multiplied by the sine of the angle because you are looking at the chordwise component. And the sine of this angle is x by root r square plus x square. So this is the distance from the axis of rotation to the point dm, and x is the distance between your point dm and the feather axis. So now with this particular concept we can write out the chordwise component of the force is going to be dm into rotation square into x. So what we have done is we have taken this equation here and substituted this part which is due to sine of the angle. So once we do that, this root term cancels with this and you are left with dm rotation speed square into x. That's the chordwise component here. So essentially like there is one component acting here and one component acting here if there is no pitch. So here there is zero pitch in terms of theta being zero. But in general, when you have a theta present, there is going to be one force acting here, there is one force acting here. And now this is the feather axis. So the distance x is from the feather axis to this mass here. And so this distance is x theta. Okay, that's x into theta using small angles. So therefore now we can consider there is going to be a moment which is generated by these two forces, and that's the propeller moment which is going to act in this manner. And this moment is going to be the mass term into x theta, and we have to sum this across the entire blade. Okay, so whenever there is a pitch angle given to the blade, there is a resulting couple regarding the feather axis, and that is going to be I theta rotation speed square into theta. So sometimes this propeller moment is also known as a tennis racket effect. And those of you who play tennis may know that if you tilt the tennis racket face, you can produce a pitching force on the ball and you can impart a complex motion to the ball because of this, which will essentially swing the ball. So that's how people use the propeller moment. Maybe they don't know it's the propeller moment, but they probably know how to use it. So now let's get all these things in one place. So we take the sum of the torques around the feathering location. And so what I have done is I have written down all these forces here. Remember, some of these forces had a moment arm. For example, here you had xi as a moment arm, so you get a square term. These were all torques actually. This is also a torque. This is of course a pure spring force. Now all these dr terms are to be summed up from 0 to r. So we integrate these terms. Now, certain interesting things you can use here. One is the fact that, remember, I0 plus mxi square is I theta. So this term will become I theta here. So I theta is here, I theta is here. Okay. And the integral 0 to r I theta dr is IF. So that's a quantity you can calculate. So we will put IF everywhere and we will simplify this equation. So essentially this equation becomes much simpler with the definition of IF, and so you get this nice looking equation here. So now this looks very much like a spring mass system. So you have a mass or inertia type of term here, you have a spring type of term here, and you have another spring type of term here and some constant terms, and then on the right hand side you have the forcing coming from the fluid mechanics forces. Now here omega theta 0 is the non-rotating natural frequency in torsion, which we have considered here, and that you can clearly see is coming from k theta here. So one of the components of frequency is going to come from k theta, which is here, and the second component is going to come purely from the rotation force, which is also the propeller moment term here. So now take this equation, divide throughout by IB into rotation speed square. So if we do that, we get this equation here where we define IF star as IF by IB. So remember, IB is the inertia in the flapping direction. And so now we clearly have the forcing term written like this, and we have the nu theta square is 1 plus this term being the term which contains the natural frequency in torsion. So nu theta is the rotating natural frequency for the torsion mode, and this of course is in per rev notation, and you see there is a component 1 which is purely from rotation, and this part is coming from the spring, so this is the non-rotating part of the torsional frequency. And this of course equation is in a pure spring mass form. So this is the spring, this is the mass, this is the forcing, this is a static forcing term. So typically what happens in torsion is that the typical blade is relatively stiff in torsion structurally, and therefore this term can be quite substantial. So what happens is that nu theta typically ranges from 3 to 10 per rev for most rotor blades. So there is a smaller component coming from the one part and a larger component coming from the spring part. So let us do some simple back of the hand calculations to get some estimates on this IF star. So let's say we have an airfoil section, but this is too complex, so let's just try to illustrate it by using a rectangular section. So consider a rectangular section with chord is C and thickness is T, and for this section I0 would be rho m into Ix plus Iz, where rho m is the density. So this is a simplified blade section we are taking here. And so in this case, I0 would be rho m into Ct cube by 12 plus Tc cube by 12. So recall that I for a rectangular section of breadth B and h height is bh cubed by 12, so we are using that here. So height corresponds to thickness and breadth corresponds to c here. So the first part is ct cubed by 12, second is tc cubed by 12. But what happens is that the term t is relatively small compared to c, so we'll neglect this term. So we only keep the term here which involves cubing the chord rather than the one which is cubing the very small thickness. So then if can be written in this form. So that is integral 0 to r rho m tc cubed by 12 dr, and so we get this here. Now we calculate if star as if by ib. So we know ib is mr cubed by 3. So we calculate this particular ratio. There are some cancellations here. So once you have performed all those cancellations, we end up with 1 by 4 c by r square. And this is going to give us an estimate about what is the size of this if star term. So for a typical value, c by r for a helicopter blade would be about 20. So if star would be 0.00063, which is a very small number. Now this fact is going to become important later when we consider coupled pitch flap motion. So if we now look at this equation here, we see that the if star here, the if star here, both of these are likely to be small numbers, but again if you solve this equation, that's all going to work out. But the interesting fact will come is that when we consider the flap equation together with the torsion equation or the pitch equation in flap pitch coupling, then certain terms can be neglected and certain things become important because of the value of the if star term. So we are going to consider that fact there. So this was the basic concept about pitch flap or pitch equation, which we are going to later use in our pitch flap and pitch flap lag models also. So what we have been doing here is that we have been looking at each of these degrees of motion separately. So we looked at the flap motion, we looked at the lag motion, and then we looked at the pitch motion. And then we are going to later in the course develop joint motion. So we are going to look at flap lag and pitch flap and then pitch flap lag. And then we are going to get coupling terms. But one of the things you can get from these pure motions is that you can look at the natural rotating frequencies clearly, and you can see the sources of the centrifugal stiffening terms which are coming into the equations. So the propeller moment, for example, is a very important effect here, and it is going to contribute to the stiffening. And the remaining part is of course going to come from the well-known structural stiffness. So I will end this lecture here. I will see you in the next video when we are going to start working on the flexible blade. So you of course realize that the actual rotor blade is not rigid. A rigid blade is a simple model of an actual rotor blade. So we will start looking at the flexible blade. See you then.